if you remember last week, we had this relation TdS minus T dV plus mu dN and whatever. So it always, the description of the energy is intensive variable and extensive variable. They are conjugated one to each other, so the same goes for P, pressure, volume, P, intensive, V, extensive, mu, chemical potential, intensive and extensive. We also have seen that we can use the Legendre transformation and transform from the energy to several other thermodynamical potentials. Like for example, F is E minus Ts. Okay, that's something that we've seen. We can have H, it was E minus plus PD, so it was minus P V. We also have Gibbs potential, we also have grand canonical potential. So different thermodynamical potentials. Why I call them potentials? Because they are transformation of the energy. So why we have to do this? Well, sometimes we don't like the extensive variables, for example, the entropy or the volume, and we have a control, better control of the temperature or the pressure or the chemical potential. So if we want to switch from one extensive variable to its conjugated intensive variable, we need to perform the Legendre transformation. Okay. And the newly obtained thermodynamical potential is going to be the variables that we like to work with. Additional stuff that we have seen is, well, the entropy is maximal, so always in equilibrium. And the energy is minimal. So it's Legendre transform F and H and G and psi. All of those are minimal. What I mean by minimal? So if we have some unconstrained variable, okay, the location of bunch of molecules, okay, so I don't really know should they be over here or over there or in some other location, right? So how we choose where to locate them? So this is the unconstrained variable, their location. We choose them such that the potential, our thermodynamical potential, if we use energy, is going to be minimal, or the entropy should be maximal. So, and all of this is in equilibrium, and you already have seen this, or it is part of it, in class on thermodynamics. Okay, some additional things that you have seen in thermodynamics is that, well, Maxwell relations, right? Maxwell relations. Yes? Constant. So accordingly, it's going to be entropy. Okay? Like for the energy is going to be entropy, the same is going to be there. The conjugated variable, that is either entropy or the variable that's conjugated to entropy. All right. What is Maxwell relation and where they are coming from? So if we have a function, a general function, let's call it A is some function, and we have dA equals to G dx plus lambda dy. So if f is an analytic function, it's continuous, we can have it first derivative, second derivative, whatever. So what do we know? G is what? Is dA to dx. Bothering me. Lambda, it is dA to dy. So if A has continuous derivatives, and continuous second order derivatives, etc., 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 we all know that dg to d y equals to what? To d lambda to dx, right? So it doesn't really matter why it is, because this is dA to dx, and here we have another dy, and here it is d to dx, dA to dy. So if all the derivatives are continuous, the order with which we take the derivatives doesn't matter, right? So it doesn't matter if we have a second derivative of a, and if we first make a derivative with respect to y and afterwards with respect to x, or we take first the derivative with respect to y and afterwards with respect to x. Okay. So all the Maxwell relations that you have seen are basically using this fact. If you have some thermodynamical potential, you write it down as a differential in this form. Okay, whatever are the functions that are standing over here in front of your coordinates, the coordinates can be intensive or extensive, depends on which potential you have chosen. You are taking the second order derivative, okay, and they're all going to be equal. So all the Maxwell relations that I've seen, they are in some sense very boring, and they all represent the fact that our functions or thermodynamical potentials are assumed to be continuous functions that have a continuous derivatives, and the continuous derivatives also have continuous derivatives. Okay. This is basically some sort of a summary of what you have seen in thermodynamics. Okay. What is our problem with all of this? The problem is it's very boring. Okay. That's the main problem. You have something very continuous, so you have all those Carnot cycles. In some sense, they're a little bit exciting, but so you have something, some kind of material, you heat it a little bit, you cool it a little bit, you shift it over here, you shift it over there. If everything continues, and you have equations that look like this, nothing exciting happens most of the time. But we do know that life is actually very exciting, and we have different state of matter. We have different behaviors that sometimes are abrupt, sometimes are unexpected, sometimes they cannot be described by some continuous modification or second order continuous derivatives. Right? So this is where we want to go. We want to describe matter at not its irregular state, where we basically do not do almost anything to it, but matter that actually transform from one place to another in an abrupt fashion. Okay, so I'll show you some short, maybe descriptions of what I mean by abrupt behavior or interesting behavior. יובל, אתה פה? בוא. Okay, so this is a guy that he decided to perform, to film the formation of bubbles in the boiling water. Okay, so he has a kettle, right? Has a kettle, simple kettle. You can do this at home. You basically boiling up the water. You have a heater inside it. It's a coil that's heating up due to electricity that runs through it. Okay, the coil heating up, it heating the bottom of the kettle. The water here heats up. They go up, all right, and bubble are formed. Okay, so we all know it from our everyday experience.
What kind of results can we get?
Okay, what kind of results? We just want to see. So this is actually a nice movie how to film those. Okay, we are more interested in the formation of what we are recording. So you can see this. This is a bubble that is formed. It's not just what you think bubble. It's something round. It's not round. It has very different and cool forms. And what is most interesting that this is water, and this bubble has exactly the same molecules as the water around it. Okay? So it's not something that is created from the heater, okay, or some junk that was inside the water and now it's expelled. It is the same material, right? So we had water, we heated it up, okay? We haven't done anything chemically, we haven't added anything, we haven't done some magic tricks. We simply heated the water, and instead of doing something like this, the same material is now looking completely different. Yes?
You say we will talk only about things that in equilibrium. But
yes, don't worry, don't worry. I won't explain to you how bubble is formed. Don't worry. There is a nucleation, non-equilibrium process. We won't talk about it. But we can talk about this matter and how they can coexist in equilibrium. Okay? They can actually coexist. So if you want to look a little bit more on those bubbles, they are actually quite fascinating. Sometimes they're round, as you can see over here. They can have different colors, depends on the external lighting, and they are fascinating. Okay, so the same matter, completely different form, completely different function, and what is important, I cannot continuously, in some sense, transform this water into this bubble. Okay? Something abrupt happens in between. Something that maybe you can say, well, it's not equilibrium, so it's not part of this class, but it's, in some sense it is. Another example, okay, so this is already a simulation. So we have a lot of particles. Some of the particles are slow, some of the particles are fast. You can think about it. All of them are located in this description. So the slow particles tend to clump together. The fast particles tend to also be together. It's like a separation. And what we see as a function of time, that although they're moving, but some particles are, the slow particles stuck together, the faster particles stuck together, and we see two phases that are emerging. One phase when the particles are moving absolutely stochastically in any direction, but some other particles that prefer not to move and just stick around, they're forming an additional phase. Now, can we actually shift the material and bring all the material from this fast behavior to this slow behavior by continuously shifting some parameter? What will happen in between? What else? Okay, so this is an additional simulation. So it's a simulation of water and oil. So we have hydrophobic molecules and hydrophilic molecules. The blue stuff, it tends to stay together. The red stuff also tends to stay together. And we have a mixture of them. So it's one phase that everything is mixed. But as time goes by, we see that all those red particles try to clump together, and we have some sort of a phase separation. So we have one kind of material, which is basically the same on one part, and all the red guys will try to clump together and face something else, something different. Okay, so you see this merging one big bubble, and after a while this guy will merge with that guy, and eventually we will have a total separation between the blues and the reds. Another simulation, also it's oil and water. Okay, so you see the red and the blue are different materials. Some materials try to clump together, then others try to clump together, and at some point the simulation won't show it. We will have a blue on one side and a greenish on the other side. So there is some saturation, an internal saturation between those guys. another nice thing of abrupt changes, sometimes unexpected. Okay, so this is called the supercooled water. The water is not supercooled, it's just cooled below the freezing point. And wait a second. Okay, so so what these guys have is they just so yeah. So this is just the water. They cooled it around -8 degrees Celsius. You see that's in a fluid phase still. So just actually flowing. And what you can say is do is that some very abrupt change can occur due to sudden change in pressure. Okay, so they're changing the local pressure inside it, and you see the freezing that actually going through the whole water at once. This is slow motion already. So at some point we have a fluid phase, one state of the material. We do like something like this, and all of the material almost immediately, this is a very slow motion, transforms into ice. Okay.
Phase transition, that's what we
My question is how those thermodynamic descriptions that you have learned last year, and I summarized on the board today, how those continuous descriptions can show something that we've seen over on YouTube today. So it's not something that I invented. It's a known phenomenon. Right. So our goal is going to be to describe, or at least to develop, a framework for thermodynamics that can describe this phase transition. How the system can go from one phase to another. Okay. And the interesting thing that happens in this phase transition, that a lot of stuff that we have learned, okay, about continuity of the relations, about some specific maximal properties, etc., etc., the part that we can go from one state to another very, very, very slowly, actually fails when we go from one phase to another. Something spectacular happens over there. You've seen this freezing bottle. It happens like at once. All the system transforms from from water to ice. So all of this description is very nice, but somehow it does not describe the way how nature works. Okay? And why it does not describe? Because the transition from one state to another happens not in equilibrium, not quasi-statically. It happens very, very, very fast. Right? But we will show that we still can use the framework of thermodynamics in order to describe the initial state and the final state. Okay? So this is where I'm heading today, and this is what we should keep in mind. So we are heading towards description of phase stability and phase transition. Okay? What I mean by phase stability, basically if I have a big system, and I will separate it into two systems. Let's call this system A and system B. This can be phase A and phase B. This can be liquid, this can be vapor. Okay? Or it just can be the same system. When the whole system A plus B is in equilibrium, there is also some sort of an equilibrium between this part of the system and that part of the system. So what it means that the systems are in equilibrium, how we describe this equilibrium property, not just by saying, well, S is maximum, or whatever. What happens to our variables, okay? Maybe conjugate variables, how they should behave. What is the connection between temperature in this part and temperature in that part? What is the connection between chemical potential, it's part A, and chemical potential, it's part B? So this is phase stability. Afterwards, we will describe how phases are actually created. Okay? So what do I mean by phase transition? Can phase A become phase B at some point? And what happens and what should happen? Okay, so here we start. So first question is, when I'm looking on two systems, that are in equilibrium. What I mean by equilibrium in terms of intensive variables. In terms of intensive variables. Okay, what I mean by intensive variables, my variables are t, my variables are p, and my variables are mu. Okay. We can have also additional variables like magnetic field and etc., but let's concentrate on those three simple examples. Okay, so how we prove whatever we want to prove, we want to use some sort of yes. What do we want to show exactly right now? So what we show is that if I have a system which have two subsystems, they can be exactly the same or they can be two different phases of matter. Okay? And they are in equilibrium. Okay? So what I mean by equilibrium, I already told you. I mean by equilibrium that there is a maximal entropy and there is a minimal energy and minimal free energy, whatever. But I don't want to say something about the energy. I want to say something about stuff that I can measure, that I can control. What happens to T? What happens to P? What happens to mu? All right. So what kind of calculation I want to perform. Now, let's assume that I do something to those systems, right? I do something to those systems, and something varies. Okay? Now, how stuff varies, I don't know, but maybe some of the particles that are in A going to become particles of B. Maybe there is some sort of a heat transfer, okay, between those particles. Maybe the pressure and so the volume is going to change a little bit from one side to another. Okay? So we have different effects that happens, but in total the system stays the same. Okay? So when the system in total stays the same, I basically say, well, if I have SA and I have VA and I have NA, okay, and for here I have SB and I have VB and I have NB. Okay? So the entropy of system A, the volume of system A, the number of particles at system A. This is the entropy at system B, the volume at system B, the number of particles at system B. I know that on total, because I kept the system in a adiabatic way, on total nothing happens. So delta S of A equals minus delta S of B. I know that delta V of A equals minus delta V of B. And I know that delta N of A equals delta N of B. Because everything is conserved. Right? I do not let heat flow from the outside. I do not let volume change. I do not let Na plus Nb change. Okay. Yes?
The number of particles should be in a minus.
Minus, thank you. Okay. Yes?
Entropy cannot grow, even though it's a...
All right. So if it's a reversible state or some sort of fluctuation, so if I haven't affected anything and the system is in equilibrium, it should be a maximum, right? So it should be the same. But what do I know? So if something happens, I can do this with entropy, but I prefer to do this with the energy. If something happens, okay, so if something happens, I know that the total change of the energy should be greater than 0. Why? The energy in equilibrium is at its minimum. So whatever happens, if those two systems are in equilibrium, whatever happens due to some fluctuations of pressure, fluctuations of number of particles, fluctuations of entropy, whatever it is, okay, still delta E should be greater than 0. Why? Because I'm in equilibrium. So any modification is basically just it's turning the energy, pushing it a little bit upwards. Okay. Now, so what happens over here? Okay. So we have T delta S A plus T, let's call it TA, plus TB delta S B plus minus P A delta V A plus minus P B delta V B plus what else we have? Mu A delta N A plus mu B delta N B. Now since delta S A equals minus delta S B, I can write down this guy as TA minus TB delta SB. The same goes over here, so I have minus PA minus PB
Delta SA, not
delta SA, thanks. Delta VA plus mu A minus mu B delta NA. Okay, now the modification of the energy always greater than 0, or at least 0, okay? It doesn't really matter by how much delta S has been modified, by how much delta V was modified, or about how much delta NA was modified. For any absolutely abstract modifications of those extensive variables, this inequality should be satisfied. It can only happen if TA equals to TB and PA equals to PB and mu A equals to mu B. Basically what I have plotted over here, have written over here, is the first variation of the energy. And since the energy is minimal, the first derivative is 0. So it is 0 with respect to S, it is 0 with respect to V, it is 0 with respect to N, and therefore all those intensive variables should be exactly the same. Yes?
Delta E needs to be negative, isn't it?
Sorry?
Delta E?
Delta E?
Negative.
Why it's negative?
Because
It's at the minima, so anything that I do will push the energy a little bit back. Entropy is maximal, energy is minimal. Energy at equilibrium, so energy at equilibrium is at minimal. Whatever I do will add something to my energy.
Okay.
Okay? Yes?
I didn't exactly understand yet why the change of entropy in A is minus the change of entropy in B, because the total should be greater than or equal to 0.
Why? If I'm saying that my constraint, my constraint is that S equals const, V equals const, and N equals const. I did something internally to the system such that the entropy haven't changed, the volume was exactly the same, the number of particles is exactly the same. Can I do that? Theoretically? So this is the claim. So at equilibrium, what we have obtained, what was our question? What would happen at equilibrium in terms of intensive variables? So in equilibrium, all the intensive variables are exactly the same over the whole system. Okay? So even if I do something like this, okay, so this is my total system. I have here V1, and I have here V2, and I have here V3, and V4, and V5, and I say all of those are subsystems of my general great system that it's in equilibrium. Because it's in equilibrium, in any place I have the same temperature, and I have the same pressure, and I have the same, exactly the same chemical potential. Mu, 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 and U. Yes. Yes.
למה לא יכולת לומר ש-TA פחות TB, כאילו ביחס זה עם הדלטה, כאילו שהם שניהם שליליים?
But okay, so the question is, can I have some other option that maybe TA is negative and TB is positive or whatever, right? Something. Can I have, so the question is, can I have a different solution than this one, right? And the answer is no, because the delta SA and delta VA and delta NA are arbitrary. I can make them whatever I want, but I still not modifying TA and TB. So I pick TA, I pick TB, I pick PA, I pick PB, I pick all the intensive quantities, and then I modify a little bit the system somehow. Somehow, okay, arbitrary, because those are arbitrary variables. This has to be, those has to be zero. So you can think about it, because those are independent, okay, those has to be zero. Any other questions? All right, so this, what happens at the equilibrium. But what happens if I'm starting in a system that it's out of equilibrium? Okay, so I modify a little bit my question over here. Yes, question.
נניח יש לי, לא יודע, איזשהו מכל או כוס עם חצי מים וחצי אוויר.
Yes.
אז המשפט הזה אומר שהלחץ של המים שווה ללחץ של האוויר?
Okay, so the question is, if I have a glass of water, and inside of glass of water I have water, and I have vapor, are there differences in the pressure of the water and the vapor? And the answer is, if the system is in equilibrium, there cannot be any differences in pressure. But you have to put them in equilibrium. Sometimes, some things cannot be in equilibrium. Water and vapor and water can. Okay? But there are some materials that simply cannot coexist together. Okay? Our simple assumptions over here says that it doesn't matter whatever it is. If it's in equilibrium, those guys must be satisfied. Why? Because we based it on our assumption of minimal energy. Okay. Any other questions? Okay. So the next question I want to ask, so this happens at equilibrium. Great. But what if I start with two systems? I have system A and I have system B. And this system has TA and this system has TB. Sorry. This is TA. So the intensive parameters are TA, PA, and MUA. And this system is TB, PB, and MUB. And this system is in equilibrium separately from the equilibrium of that system. They are distanced from each other, they're not touching each other, there is no flow of heat, nothing. Okay, so this is equilibrium A, this is equilibrium B. Somehow now I make a contact between those two systems, and I allow the heat to flow from one system to another. I close the outside world, and the outside world is not affecting the two systems anymore. They now equilibrate somehow. Okay? Now they equilibrate somehow. So at some point, after a while, okay, our assumption is, after a while, the temperatures of system A and system B are going to be the same. The pressures of the system A and system B is going to be the same, and the chemical potentials of system A and system B are going to be the same. So we start when they are not in equilibrium. We put them in contact, and after a while, equilibrium occurs. I'm not telling you how much time it's going to take. It's going to take forever, as long as I care. But eventually, okay, my assumption is they will reach equilibrium. So the question is, what will happen? So the entropy will flow from where to where? Or the heat will flow from where to where? The volume is going to change volume of this system or that system? The number of particles are going to change from where the particles are going to flow, from system B to system A, or from system A to system B. Okay. How I obtain those simple relations of what happens at equilibration? Yes.
Is that true for any intensive variable?
Yes. Any intensive variable.
So if I will just think about intensive variables that for each one of them, right?
Sorry, say it again.
Oh.
בעברית אם אתה רוצה?
אתה הוכחת לכל אחד מהמשתנים האינטנסיביים האלו.
Yeah.
נכון? אבל לא הוכחת למעשה שלכל משתנה אינטנסיבי.
So, if I had, so the question is as follows. Stas, you have proved to us that for those three intensive variables, they are exactly the same. Okay? If I will have another intensive variable, okay, and the answer is I would add an additional extensive variable on their conjugated representation in the same way. Let's call it, I will have d delta f of A, and I will have here delta g of, some GA minus GB. What will happen if I had additional extensive variables, let's call them F, they will have conjugated intensive variables, I call them G, and they will add an additional form that looks like this, and in equilibrium, GA will be equals to GA. It doesn't matter what kind of variables I have, as long as I have this representation of intensive multiplied by extensive. Yes?
You say that E is minimal and the next is constant, right? So how can you say again that delta E is greater than 0 if we let us...
So you do something. Something happens in the system. The system is in equilibrium. Something happens. In equilibrium, we had a very specific representations of the subsystems.
Specifically about the delta S. How can we let delta S
to be constant, 0. So you want me to explain the experimental setup?
אנחנו אומרים ששינוי משקל, E מינימלי,
Yes. Yes. E minimal for what? For a constant S, right? So if I have delta S equals to minus delta S equals to minus delta SB. S is constant. The question is as follows, right? So E is minimal for what? For a total constant entropy of the system. Have I modified the entropy of my system when I done this? No. So E is minimal. Right? S is kept constant. Yes?
Isn't E only minimal locally? So
Globally.
But if I have something like this...
No, you don't have something like that. You have a global minimum. This is an assumption. The system has to reach a global minimum. So, for example, this experiment that I have shown to you, that the bottle of the water, it was water, right? The water was at minus 8 degrees Celsius. It wasn't ice. How can this be? Right? It was in a local minima and not a global minima. In a global minima, the water has to be ice. Okay, it's a different aspect. Let me concentrate on this, right? So
So for our purposes,
all right. Let me continue, right?
It's like analytical.
What do you mean by analytical? So, the assumption is if you have an E of X, eventually it will reach over here. Right? So, and the first derivative has to be 0. And those are the first derivatives. Whatever stands over here. This is why it's 0. Okay, let me continue. Otherwise, we will be stuck with this minima and maxima forever. Don't worry, we have some other stuff to do. Okay, so first of all, what happens? So when I let the system equilibrate, so delta SA plus delta SB equals to delta S. Right? Are you with me? I don't know what happens to the entropy over here and entropy over there, but the total change in entropy is the change of the entropy of system A and the change of entropy of system B. This is the total entropy. Okay, so since I close my system and the outside world is not affecting, so the process as a diabatic, eventually at equilibrium, because I start out of it at some specific state, I reach the final equilibrium state due to a diabatic process. There is no exchange of heat from the outside world. This has to be greater than 0 or greater than equal. Okay. No, I don't care. I don't care. I have two systems. I have heated up this eraser, I cool down this marker, I put them together in a chamber, all right, so no flux of heat outside, nothing affecting those two guys inside the chamber, and I ask what happens after a million years. That's the kind of question. If the human race survives another million years. Okay, so delta S is greater than 0. What is delta S? What is delta S? So we can have that is ds A dE delta E A plus ds B dE B delta E B. Now, so this occurred because the system is closed. Delta E, which is equals to delta E A plus delta E B equals to what? 0. It has to be equal exactly to 0. Why? Because I haven't let any energy to come inside the system. Okay. So what we have over here, what is dSA to dA? What is dSB to dB? 1 over temperature. 1 over TA minus 1 over TB delta E A greater than 0. So this equation is enough in order to decide where the heat is going to flow. Okay, so if TA is greater than TB, 1 over TA minus 1 over TB is what?
Negative.
1 over TA minus 1 over TB is negative. Okay? Which means delta EA is negative. Okay? So if I have the temperature of this guy is greater than the temperature of that guy, okay, and the only thing that I let happen is for the heat to flow from one part to another, the heat will flow from hot object to cold object, right? Okay, so this is what we got. The other way around, TB smaller than TA smaller than TB, 1 over TA minus 1 over TB is greater than 0. Delta EA is greater than 0. So, if this object is colder than that object, heat will flow from here to there. Okay. So, this means that I can do exactly the same for pressure. I can do the same argument. And for chemical potential, right? And what will I obtain? I will obtain that if I have difference in temperature, I will have a flow of heat from hot object to cold object. If I have difference in number of particles, I will have a flow of particles from what object? From object with higher chemical potential to object with lower chemical potential. If I have two objects, with one is at high pressure and another one at low pressure, okay, I will have a flow of volume, okay? There will be a modification of volume due to the differences in what? In the intensive variables. So they act as forces, right? So I can think about it in the following. This TA is larger, is smaller. There is imbalance between the intensive variables. Those intensive variables are what? Are my generalized forces. And I want to reach eventually a balance of those forces. Okay, so TA, or temperature, and mu, and pressure. We already had given the name, which are generalized forces, but the exact name are thermodynamic affinities. And at equilibrium, all the affinities are exactly the same all over the system. In order to reach equilibrium, we will have a flow from a higher affinity to a lower affinity. A flow of what? Of the variable that is conjugated to the affinity. For temperature, it is heat. For chemical potential, it is number of particles. For pressure, it's the volume. Eventually, everything equilibrates. At equilibrium, the affinities are exactly the same. The volume are not the same. The number of particles are not the same, and the energies are not the same. Right? The energies are not the same. But those guys, it's like equilibration of forces, has to be exactly the same. From where to where the heat flows, from high temperature to low temperature. From where to where the number of particles flows, from one chemical potential to the lower chemical potential. Everything eventually goes down. Yes?
Are you saying the extensive parameters are changing to adapt the intensive?
So eventually, yes. So the differences in intensive parameters are creating a modification in the extensive parameters, such that eventually there will be an equilibrium that is described by equivalence of all the intensive parameters over the system. Yes? I have no idea how to translate this word into Hebrew. Affinity. This is how it goes. I have no idea. Don't ask me that. I have no idea. Well, I know what is integral in Hebrew. I know what is integral in Hebrew. There is a word. I don't know if there is a word for affinity, but for integral there is a word, but we don't use it, right? What is the word for integral in Hebrew? Askemet. Nobody uses it. Okay, so we can use it. Thermodynamics, affinities. You don't like the word, you don't have to use it. It's fine. But if you look at if you will see in a book thermodynamic affinity, you will know that they mean to intensive variables of the system. That's all. It's the same. The same. Intensive internal parameter is the same as thermodynamic affinity. The same. Any other question? Yes?
Why you say that? כאילו למה אמרת שלבסוף הטמפרטורות תתייצבו?
Because I know that at equilibrium they have to be exactly the same. Shh. Okay. At equilibrium the temperatures have to be exactly the same. I've proven that, right?
אז איך אתה יודע שהטמפרטורה השנייה לא פשוט תעלה לראשונה?
I don't know how it will happen, right? I'm not describing to you the process at eternity. I know what happens at the end.
לא, אתה אומר אבל שהטמפרטורה תרד או תעלה?
I am not, look, what I have told to you, that I haven't told that TB is going to go lower or higher. The only thing that I told you is what is going to happen to the energy. Eventually, something will happen to the temperatures. Other questions? Shh.
Are linearly dependent, right, between each other?
Okay, they can.
They are or they are not?
So what? The entropy and the volume, there is a dependence.
The temperature, the potential, the chemical potential.
It depends on, so if you have an equation of state, the equation of state that describes what is your equilibrium connects somehow between the extensive parameter variables or the intensive variables. So there should be some sort of a connection between those due to this equation of state. So for example, the simplest example is the ideal gas, right? There is a connection, PV equals NT, right? So there is a connection: pressure, volume, temperature. Why? Because this is this material, and this is how it's described. A different kind of material, van der Waals gas, going to have different connection. Okay? Depends on the material. Great. So what we are going to do next? The next thing is to develop some additional description of what happens at equilibrium, whatever. So it is the stability of the phases that we are still interested in. So again, I have two systems. I have two systems. Okay. There is some sort of a separation, a system A and a system B. Okay. And I claim that they are in equilibrium, and I claim that my equilibrium is stable. What do I mean by stable? Right? So how actually I say what the equilibrium is stable? I'm saying that if I keep the system like that, and I won't really do anything to it, it will be exactly at the same state. Right? So the equilibrium state is defined by extensive and intensive parameters. So the system reached equilibrium. A somehow is equilibrated with B. Okay? And I'm claiming that as a function of time now, nothing is going to happen. Right? Now, but there is always something happens. Right? So I've shown you this simulations. Some molecules from A are going maybe 1, 2 out of the Avogadro number of molecules, 1, 2, 3, 4, okay, are going to cross and switch into B. And some maybe molecules from B will switch to A. Or a little bit of a heat that was in A will flow back to B, or from B to A. There are always, as we know, modifications in the world. So nothing is really constant. There are tiny, tiny changes that happen all the time. But still nothing happens to the system. This is stability. Okay? So those small modifications can drive the system out of equilibrium. But the system still stays at equilibrium. This means that the system is stable, that the equilibrium is stable. What do I mean by stable? So if you remember the class of analytical mechanics. Okay? So if you look on the system, I have a rod and I have a mass. So it's a mathematical pendulum, not on a string but on a rod. Okay? And it can rotate in a circular motion. Okay. So it can do something like this, and if I provide it enough sufficient kinetic energy, it will start to do something like this. Okay. Now, for this system, there are two equilibrium positions. What are the two equilibrium positions? Theta equals 0, right? Why? Because the total amount of forces exactly over here is what? Is 0. Okay, so I have, let's call it N from the rod, and I have mg, and if the rod is exactly at this position, right, there is an equilibrium, and sigma f equals to 0. This is my equilibrium. Another equilibrium is where?
At the top.
Pi over
Pi.
just pi. Okay. Over here, it's also an equilibrium. I will have N over here, I will have mg over there. Okay. Both of those guys cancel each other out, and I have sigma f equals to 0. What is a stable equilibrium and what is not a stable equilibrium? This is stable?
Yes.
This is a stable equilibrium. This is unstable equilibrium.
Yes.
Yes.
מה שלמדנו שכאילו בגרף של הנגזרת השנייה זה כאילו...
I will talk about in a second. I will talk about it in a second. Okay. How do we know that this is a stable equilibrium? What it actually means? So when the rod is located at this position, if I shift it a little bit to the left or to the right, the pendulum will come back to its equilibrium. Okay. So small modifications, they will create oscillations, but never mind those. Okay. So if I shift my pendulum to the left, or to the right, it will come backwards to the equilibrium position. Unlike this guy, right? So if I put my pendulum upwards and I shift it a little bit to the left, a little bit to the right, and it doesn't really matter by how much I'm going to shift it, it's going to go far away from the equilibrium point. Okay? So this can be understood if we plot the energy of the system, or potential energy actually, right? So the potential energy, this is theta, this is U of theta. So the potential energy looks like this. This is 0, this is pi, and this is minus pi. When I'm putting my system over here, that's at a minimum of my potential energy, this is a stable point. Why do I know that it's a stable point? Because it's a minimum. I shift my particle a little bit to the left or a little to the right. The force is what? The derivative, minus the derivative of the potential energy. So the force is a restoring force, and it's going to bring me backwards to 0. If I put my particle at this position, so this is upwards, okay? If I shift my particle a little bit to the right or a little bit to the left, it doesn't matter if it's only one molecule, 2, 3, 4, or a very small amount of heat that are actually modifying my position. The particle will run away from the equilibrium. Stable, unstable. Okay? So when we look on physical systems, if I look on this marker and I won't move for an hour, nothing will happen to the marker. It is in equilibrium, unless I will open it up, and then some process, chemical process will start to happen. But if I look on this marker, it's in equilibrium, nothing happens to it. It means that equilibrium is stable, and it somehow should be described by this guy. But we already know that. We know what? We know that the energy is at minima, or we know that the entropy is at maxima. So can we use those properties in order to say something about the stability between two phases? If I have phase A and I have phase B, what is the fact that I'm at some general potential located at a minima, okay, or if it's entropy, it's a maxima, what it's actually saying about my intensive variables, right? I know that the intensive variables of A are exactly the same as intensive variables of B. But if some modification happens, some fluctuation, or I push my system a little bit from the equilibrium. So there should be some connections between the intensive variables, or how they are modified, in order for the system to be stable. Okay? So those are the connections that we are looking for now. Because I've told you that there is the same value for all the different intensive variables. This is equilibrium. But the only fact that I used that the first derivative is 0. If you look, I only told you that delta E was equal 0 eventually. This is the first derivative. Right? But if it's a minima, I should use also the property that it's going to be positive. Right? So if I'm going away, the second derivative should be positive. And we haven't used this fact at all. So this is what we are going to use now. More of entropy, but we'll see. Yes, question.
לגבי השינוי הקטן שאתה מדבר עליו, שאם אני משנה את זה טיפה, אז יכול להגיע למצב אחר. אמרנו שהשינוי הכולל, כאילו, כשאתה אומר מערכת, השינוי הכולל של המערכת הוא 0. בפנים, היא משתנה אולי טיפה, אבל הכולל הוא 0.
Yes, but the energy can be modified maybe. Something happens internally. Okay, let's assume that the energy, there is a fluctuation of a kinetic energy of one specific particle. It can happen. So there is a fluctuation of one molecule out of 10 to the power 23. It's a modification, and the total energy is going to rise up a little bit. It's a small fluctuation. I'm not saying that it's going to be big fluctuation, but it's small fluctuation. Or I'm driving the system a little bit out of equilibrium. I'm driving the system a little bit out of equilibrium. And I'm going to say, to see how it's going to go backwards. Alright, so what we want to do is as follows. Let's assume that we have two systems. Okay, have U and V and N, and those two systems are exactly the same, and they live in equilibrium. I do something to those systems. Okay. Somehow, okay, theoretically, I'm going to decrease the energy of the left-hand system by delta E. I will keep V and N exactly the same. And I'm going to increase the energy of the right-hand system by delta E. Okay. I will explain in a second what actually happened. Why I have done that. Okay, so this is an equilibrium. I have done something to the system, right? And then, after I have done it, I let the system be. Okay. So what do I know? What do I know? That if I have done something to the system and then I left it alone, eventually it will have to equilibrate because I started from equilibrium. So if I let the system be, it will equilibrate and will become this system that I described over here. And I want to use this fact in order to say something very, very, very strong. Okay. So if this is the energy, and this is the entropy of the system, how do we think that our entropy should go with energy? So we already know that, right? Entropy is a monotonically growing function of entropy. So can it look something like this?
No.
Why?
Because the second derivative is not original.
Oh. So there is already an answer, but there is a better answer. Right? There is a better answer. How this function is called? This is a convex function. Okay, there are two types of functions. There are convex function and concave function. Concave function. Okay, in Hebrew, it's the opposite of what you think. Okay, how you remember the names in Hebrew? It's always the opposite. So this is convex. So this is k'mua. And this is concave. This is ki'ura. Why is the opposite? So ki'ara in Hebrew, it's a ball. You always think, oh, it's ki'ara, ki'ura. So it should look something like this. But no. Okay. So k'mua. This is k'mura. This is ki'ura. It's a four. So ki'ura looks something like this. K'mura looks something like that. So in Hebrew, it's very easy to remember. It's just the opposite of what you think. If you have to guess, you guess, and then you can wrong. So how I describe this k'mura and ki'ura and why I need this concave and convex description. Okay. So if this is U, I'm sorry, E. This is E minus delta E. This is E plus delta E. This is S of E minus delta E.
This is with keeping the rest of the variables constant.
Yeah,
yes.
so everything else is constant. V is constant, N is constant.
Okay.
This is S E plus delta E. Okay. And this guy is S of E. Okay, so we have three values. The original, I used here U, not E, so this is U. This is me writing some funny stuff. Okay. So why this convex and concave? So if we connect those two dots, we see that this point, okay, this point is what? It is SE plus delta E plus SE minus delta E divided by 2. And what we see is that this point, for the case of convex function, is greater than S of E. Right? So if I had the dependence of entropy, so it's a monotonically growing function, which is fine, right? So S is monotonically growing function of E, but I'm going to say it's a convex function, okay? So if it's a convex function, this will always has to be satisfied. This is a definition of convex function for me, right? So if this is satisfied, I have that SE plus delta E plus SE minus delta E is greater than 2S of E. Right? Yes?
The graph you drew is not convex or concave.
In this region. In this region.
But,
okay. Okay? All right, so what we have reached? Too many mathematicians in the class. So what we have reached? We have reached, look, that what is this, the total entropy of this system in equilibrium? 2S of E, right? What is the system or the entropy of this system? This is E minus delta E plus S E plus delta E. And what my claim is that if the system or the function is convex, the entropy of this system that I created, okay, by some modifications, is greater than the entropy of this system. So, where the equilibrium will, how the equilibrium will follow. So what I have claimed previously, that since the system here is in equilibrium, my modifications eventually will die out, and the system will reach this state. But in this state, the total entropy is lower than in the perturbed state.
Oh no.
Oh no, yes. So what it means, this means that whatever is described over here cannot be true. Okay? So the function cannot be convex in any portion of in any range of E. Anywhere that I go, I can make this argument. Okay, I can make this argument and say, well, it never happens. What actually have to happen is that SE plus delta E plus SE minus delta E is smaller than 2S of E. Okay. This is the description, or let's write it like this: SE plus delta E plus SE minus delta E divided by 2 is smaller than S of E. Why? Because I want to reach eventually this state. This means that the entropy in this state is larger than the entropy of that state. Right? And this is a concave function. So what we have reached eventually, that in equilibrium, any dependence of my entropy on energy is not just a monotonically growing function, is also a concave, the other way that I was thinking about, the concave function. Okay? Questions? So mathematical fact, right? So if we assume that there is a principle of maximal entropy, there is also a principle of concave form of the function. The moment that we have concave description, so this is a global description, not local, global. We can go to a local description. So let's write down this guy in the following form. So we can make an asterisk over here. So the asterisk says that SE plus delta E minus 2SE plus SE minus delta E smaller than 0. We have here S of E plus delta E minus SE minus SE minus SE minus delta E. This is smaller than 0. Let's divide everything by delta E. Okay. So what we have over here, we have S prime of E plus delta E minus S prime of E smaller than 0. We divide again this guy by delta E. So we have D squared S D E squared smaller than 0. This is a local description, and this is a global description. This concavity leads to local behavior of the derivative, not the other way around. Okay. So this is important to say that the function is concave, and from this concavity we can obtain this local behavior. Local behavior does not always mean that the function everywhere is concave. Okay, so this is for S. What will happen for U? So basically what I'm saying is that I cannot display S as a concave function. So I can use again what happens to U. Now, we can use exactly the same argument as for E. So if S satisfies, not U, it's E. So if S satisfies this guy, right? For E is the other way around. So E of S plus delta S plus E S minus delta S is greater than 2S of E, 2E of S. One is minimal, the other is maximal. The maximal brought us here. The minimality of energy will bring us over there. Okay? So this is again global condition. So if S is concave, E is convex. Now we can go forward and say, well, let's describe the local parameter. Okay? I'm going to do exactly the same. I'm going to say this is ES plus delta S minus E of S minus E of S minus E S minus delta S smaller than 0. I'm sorry, greater than 0. And this means that d squared E to ds squared is what? Is greater than 0. This is local condition. Now, how does it help us? Okay. Why do I need this global, local, or whatever? What do you think? What is dE to ds? Temperature. T. So what do I have? I have d squared E to ds squared, which is greater than 0. It means that dt to ds is what? Is greater than 0. Okay, very nice, Stas. You have worked a lot, and I don't really know what this entropy is, so this condition is actually useless for me. Okay? But I can repeat all my reasoning, right? Repeat everything for E and V plus delta V minus plus E of V minus delta V. Okay? So replace at any position that we have entropy by volume. Okay? What we will get? We will get that d squared E to d V squared is greater than 0. Okay. But what is dE to dV? Minus P. So d dV of minus P greater than 0. This is already something that I can use. Now, where is this satisfied? And the answer is everywhere. We obtain this relation from the convex properties of the energy. So we show this for energy and entropy, but the same argument works for energy and volume, energy and number of particles, energy and whatever other extensive parameter that you have. We will always obtain a convex property, and the moment we have a convex property, we can have a local description of how the energy behaves with the extensive parameter. It's going to be positive, and we are done. Yes?
But with entropy, we have the whole second law, I think, that tells us that the entropy is getting lower.
And energy is? And the energy is? It's minimal. The same works for this.
But we can't. We can't do the trick that the entropy is getting lower if it doesn't happen.
I can.
We can do this for entropy, but for volume. But for volume,
it's the same trick. I can show it to you later, but it's exactly the same trick.
Why the volume also need to always increase?
Because due to the form of the energy. Okay. If you want, I can show it to you later. All right. But it's the same trick. You take the energy. You take the energy. The energy is at its max, at its minimum. Okay. So you can think about it in the following aspect. So if the energy is at a minimum with respect to any unconstrained parameter, okay. So I'm going to say that volume is unconstrained. Okay. So I have two systems, and I somehow unconstrain the volume. Okay. So if the volume is unconstrained, the energy is going to be maximal. The maximal is going to say that I will have minimal, I'm sorry, that I'm going to have a positive second derivative. I can use this. All right? But it's actually stronger because the convexity property. Okay, so where it leaves us? It leaves us with the following description. We can take an intensive parameter and compute the derivative of this parameter with respect to its conjugate variable, extensive parameter. Okay. The derivative has to be positive. Okay. This is what have we shown. So, for example, if I'm going to take d mu to dn, it's going to be positive. This is an intensive variable. This is the conjugated extensive variable from what I have shown to you. Okay, the derivative of this guy with respect to that guy is going to be greater than 0 in order for the system to be stable. Okay? What I mean is that if I push the system out of equilibrium a little bit, the system will come back to the equilibrium. Why? Those are the properties that have to be satisfied, and they are going to modify whatever perturbation that I impose on the system. Samud. So, but for example, if I'll ask you the following, what is dp to ds? I have no idea, right? Because it does not satisfy whatever is written on the left-hand side of the board. I have to take, this is of course, it's intensive parameter, variable. This is extensive, but they are not conjugated, right? P is conjugated with volume, not with entropy. So those are stability criteria that we need to satisfy for any function. So what we have learned so far we're saying the following thing. If we have two systems, A and B, for those two systems to be in equilibrium, the temperatures are going to be exactly the same. The pressures are going to be exactly the same. And the chemical potentials are going to be exactly the same. But it's not just that. It's not just that everything is equal. Is when I have fluctuations, when I have small perturbations, when I have some sort of modifications of the system is going to flow backwards towards equilibrium. What is actually making it flow backwards? The behavior of the intensive parameters. So when there are some fluctuations in what? In volume, in number of molecules, what can actually be changed? It's not that the pressure is going to be modified. What is modified are extensive parameters. Volume, number of particles, a little bit of heat that flows in or flows outside. Okay. Due to the properties of the intensive quantities, how they are modified with those modifications, the system is going to be kept in equilibrium. Now, this is what's going to help me to understand how phase transition occurs. So, remember, what was my goal? My goal was to describe situations when there are abrupt changes, abrupt modifications of the total behavior of the whole system. It's not that I heat the system a little bit, or I cool it a little bit, I make some more pressure, I release the pressure. I want to see how the system responds to big modifications. Right? Now, I cannot do this dynamically. I cannot say, well, what happens to each molecule in the system? But what can I do? I can say, well, let's assume the following, that I will have here water, and I will have here vapor. Right, so those are two completely different phases of the same material. I have a lot of air here, a lot of bubbles, and I here have water. Now, if I place those two systems in equilibrium, and I will look what happened between them, or how exactly they are in equilibrium, right? I can maybe understand how this phase transition occurs. Okay. So I cannot describe to you dynamically what happens on the level of each molecule. Okay. So there's a lot of mixture of different stuff that's going on, and there are crystallization and nucleation and all different Asians, right? But eventually, we will have two systems that are in equilibrium, phase A and phase B. And those systems have to be in stable equilibrium because I can keep them like that and nothing will happen. And by studying those equilibriums, I can maybe, this is my hope and this is my goal, understand when phase transition occurs, maybe how it occurs, and maybe what happens exactly at phase transition. Okay? I want still to use the thermodynamical prescription. I cannot use any dynamics. I only can say, well, in equilibrium, all of this stuff that I have written to you still applies. So let's try and figure out if a phase transition occurred. So indeed, water transformed into vapor, or water transformed into ice. A magnetic system transformed from paramagnetic to ferromagnetic. I will have a superconductive behavior. Somehow, I don't know how it happens. But if those two systems somehow kept in equilibrium, those guys have to be satisfied, and maybe they can teach me something about the phase transition itself. I won't be able to describe to you the dynamics of the phase transition, but I can describe to you what happens at equilibrium for the phase transitions. Okay, so we will continue on this on Tuesday. Thanks. זה הקונג'גט, זה לא הטרנספורמר ז'אנדר שלו, זה המשתנה הצמוד.
לא צמוד שמאוחר.
לא. נניח היה לך E שווה ל-EDS מינוס PDB. S צמוד של T, P צמוד של B.
אין משהו מסתרת
של B. תשים לב, כשאני רושם את הדיפרנציאל, סליחה, אני רושם את הדיפרנציאל של E, אני תמיד רושם את זה בתור משתנים אינטנסיביים, משתנים אקסטנסיביים, והם מצומדים אחד לשני. חייב להיות והם מצומדים אחד לשני. כשאני אעשה טרנספורם לפלט, כמו שאתה אומר, F, אז יהיה לי SDT. אוקיי? כן. אני אומר זה אפשרי. זה אפשרי. אני טוען שזה אפשרי, כן? מה קורה אז? מה קורה בתהליך הזה? כלומר, בגלל ששתי הפאזות האלה יושבות באיזשהו שיווי משקל, אז מה שחייב להתקיים ביניהם זה שוויון בטמפרטורות, שוויון בין הפוטנציאל הכימי. השוויונות האלה איכשהו ילמדו אותי על מה קורה בפנים. כי למה אני יודע? כי נניח המיו שווה, אבל נניח אני אזיז את המיו קצת שמאלה או קצת ימינה. בגלל הקשרים האלה שהנגזרות האלה של חיוביות, הם יגידו לי משהו לגבי השינוי של מיו במעבר פאזה.
חשבתי שכאילו אני מנסה להגיד לנו שהמצב של במים
לא, הפוך. אני טוען שהכל יציב. הכל יציב. כל עוד זה לא יציב. אבל הכל יציב. והמעבר, איך אני לומד על המעבר מפאזה א' לפאזה ב'? כשאני לומד, מסתכל על המצב היציב הזה ומה קורה לכל מיני פרמטרים אינטנסיביים פה ומה קורה לכל מיני פרמטרים אינטנסיביים שם. כי אני אשווה אותם.
בסוף אתה תשווה
עכשיו, לא. אני מניח כזה דבר. כל הפאזות בטבע יכולות להיות בשיווי משקל אחת עם השני. אני מניח את זה, כי כל תרמודינמיקה וגם מכניקה סטטיסטית מניחה שלא משנה על מה אנחנו מסתכלים, בסוף זה יגיע לשיווי משקל. אז נניח שיש לך חומר כמו מים, הוא יכול לעבור מעברי פאזה, הוא יכול לעבור והוא יכול לעבור לאוויר, הוא גם יכול להפוך לקרח כמו שאנחנו רואים. ואני לא יודע להסביר דינמיקה כי אין לי שום דבר. הכלי היחידי שיש לי כרגע בידיים זה מה קורה בשיווי משקל, ועוד בצורה די נוראית עם המשוואות התרמודינמיות האלה. אני חייב להניח כדי לפתור בכלל משהו, אני אומר, או שיש לי פה איזשהו מאמר רציף אחד לשני, או אולי יש פה איזושהי קפיצה, ואני ראיתי בניסויים שקיימת איזושהי קפיצה, אבל אני כן חייב להניח שקיים שיווי משקל, קיים שיווי משקל, ומתוך הקיימות של שיווי משקל אני אצליח להוציא נפלאות. לא אני, אבל אני כבר הראיתי משהו כזה. אני אשתמש בנגזרות. בסדר?
כאילו העולם יותר מסובך מזה שאתה מניח תמיד במצבי צליל.
נכון, לכן תרמודינמיקה עובדת במקרים של שיווי משקל, אבל מתברר שגברים מתים היא מתארת לא רע. זה לא יתאר לך מולקולה, זה לא יתאר לך חוקי, זה לא יתאר לך חוקה, את הכיתה, התנהגות בכיתה זה לא יתאר, אבל יש לא מעט חומרים שזה כן.
זה שריטה ברור.
כלומר, אנחנו צריכים לדחוף את המערכות לשם, זה נכון, רוב התהליכים בטבע הם מחוץ לשיווי משקל, אבל אם אני אקח מים ואני אחמם אותם קצת ואני אשמור על החום שלהם ואני לא אתן לאוויר לברוח בסוף, יצטברו לי פה מים ויהיה לי פה אוויר וזה יהיה בשיווי משקל, ואז מתוך השיווי משקל אני אלמד משהו. כן. זה אתה יכול לקחת.